In this video, we're going to simulate a 2D ideal gas in Python. So we're actually going to animate the molecules of our gas colliding with each other and with the walls of the container, and we're going to see if we can recover the Maxwell-Boltzmann distribution. So remember, when we have a 2D ideal gas, the speeds v of the particles in the gas are known to follow the Maxwell-Boltzmann distribution, which is given by this f of v down there, where m is the mass of the particles and kBt is the average energy per particle. So this is actually what we're going to try to verify with the data from our simulation. So to make this simulation, we need to state a few assumptions, right? So the first assumption we're making is that the particles are represented by circles that all have the same radius and mass. The particles start at random positions with random velocities. The number of particles in the container remains fixed throughout the simulation, and the particles can collide elastically with each other and with the boundaries of the container. So with these assumptions in mind, we can actually come up with a simple algorithm that implements this ideal gas simulation. So what we do is we fix the number of particles, the size of the container, and the duration of the animation. Then we initialize our particles' positions and velocities at t equals 0. And what we need to do is at each time step, so to evolve our particles, we need to find the particles that are colliding with other particles or with the walls of the container. And when we find these particles, we need to update their velocities to account for the conservation of energy and the conservation of momentum. And once these velocities have been updated, we can actually compute the positions of our particles at the next time step using this equation, right? So r of t plus delta t is r of t, so the position at time t, plus the updated velocity times a small time increment delta t. So this is basically what we're going to be implementing. So when our particles are colliding with other particles, we're going to use these following formulas that account for the conservation of energy and momentum, and I actually found them on Wikipedia. And then when the particles collide with the walls, we need to invert the component of the velocity that's perpendicular to the wall, right? So that makes the particles bounce off the wall in the other direction. Okay, so now that we've set this up, we can actually start coding our simulation. So we just need three libraries: NumPy, Matplotlib, and itertools. So let's run this. Okay, so what we're going to do is we're going to create a class called ideal gas that's going to store all the methods and attributes and functions for this animation. So I've written a part of the initialize block down there, and as you can see, it takes in several arguments. So n, the number of particles, the mass of the particles, the radius, the length of the box, v0, which is the initial velocity, the duration of the animation, and the number of steps in the animation. Okay, so I've initialized all of these variables over there. And as you can see, I've also put the units I'm using. Okay, so it's always good to try and include the units you're using when you define variables for any kind of scientific computing. Okay, and I've also added this variable called dt, which is the small time step delta t that I mentioned above. And that's just the duration of the animation divided by the number of steps. Okay, so now that we've initialized these basic variables, we need to set up our particles' random positions and velocities at the initial time. Let's start with initializing the positions. So when we do this, we have to be very careful to make sure that the particles aren't overlapping, right? So what I mean is that the particles are sitting on top of each other, that they have the same position, because that's basically unphysical. And if that happens, and you can try to let this happen, you'll see that during your animation, you'll have numerical errors and you lose things like conservation of energy. So we need to make sure that the particles aren't overlapping. And the best way to do this is to put them on a regular grid. Okay, so we're just doing this at the initial time. So to do this, I'm defining the length of the grid. Okay, so it's just the ceiling of the square root of n, so the closest integer rounded up from the square root of n. And then the spacing, so the distance between particles in the grid is just going to be L over the grid size. And then I create a bunch of equally spaced x coordinates. I do this with numpy.linspace, starting from this position, so radius plus spacing over 2, and ending at this position. Okay, so I'm not starting this at 0 because I want to make sure that none of the particles are too close to the edges of the box, otherwise they can stick out. Okay, so once I've got these x positions in the grid, I just get, all the combination of x with itself, and that gives me all the x and y coordinates in the grid. And then I create an attribute called self.r, which is basically an array of size n times 2, right? So I'm only keeping the first n points in my positions array. And this is basically an array containing the 2D vectors, the 2D position vectors for all of my n particles. So it's an array of size n by 2. So what we can start by doing is just running this first block to see if our code is working fine. Okay, so I've added this code that actually creates the class with 10 particles. And then I also added the other variables. And what I'm doing here is I am basically plotting all the x and y coordinates in the array gas.r. So let's see what happens if I do this. Okay, so you see I do get all my 10 particles in this nice grid. So maybe let's try with 100 to see how it looks. So yeah, see, we're able to create all these particle positions without having them overlap. So far so good. So now that we've done this, the next thing we need to do is we need to initialize the velocities. So to do this, what I'm going to do is I'm going to have all of my particles start with the same velocity magnitude, which is going to be v0, but all the velocity vectors are going to be pointing in random directions. And the reason why I'm having them all start with the same magnitude is to basically make the evolution towards the equilibrium when we do the animation more visible. Okay, so the way we do this is we create a bunch of random angles. So theta equals numpy dot random dot uniform from 0 to 2 times numpy dot pi, and I'm going to create n random angles since I have n particles, and then I create the x and y components of each velocity vector of my particles, right? So the x component are going to be given by v0 times numpy dot cosine theta. The y components are going to be given by v0 times numpy dot sine theta. And then I can just create the attribute self.v, which is again going to be an array of size n times 2 that contains all the velocity vectors of my particles by stacking vx and vy. So numpy.stack vx vy along the first axis. Okay, so this basically gives me an array of size n by 2, right? So I can let's see this. So gas.v is basically, right, so this is the velocity vector for each particle. So there's two numbers because we're in 2D. So now we've gotten this out of the way, the next thing we need to do is we need to write this function called check collisions that's basically going to be called at each time step of the animation, and it's going to check for particle collisions and particle wall collisions, and when it finds collisions it updates the velocities of the particles in question, accounting for the conservation of energy and momentum. Okay, so this is the most important function because we're going to need to call it at every single step of the animation. So the first thing I'm doing is I'm computing rnext, which is the positions of the particle at the next time step, and I'm going to use this to check if collisions are due to happen. Okay, so the first type of collisions that we're going to handle are going to be the wall collisions. Okay, so in the wall collisions, we have to notice that there are 4 different cases. So a particle can collide with this wall on the left. So if it collides with this wall, it needs to bounce off. It can collide with the wall on the right. It can also collide with this one or with the wall that's up. Okay, so there's 4 different cases. So what we're going to do to update the velocities of the particles that are colliding with the wall is I'm going to do the following. So I'm going to go into the array self.v, so the positions of the particles, the velocities of the particles at time t, and then I'm going to find the particles that have an x components. This is what I'm doing when I'm doing rnext with the 0 in the second index. I'm finding the particles with an x component that's less than radius, that's then self.radius. So I'm finding the particles that are within a distance radius of the left wall. Okay, and then I pick the x component, so I do this with the comma 0, and then I just multiply it by -1. And this basically makes sure that the particles are reflected. So maybe let's do a quick demonstration of what I've just done. Okay, so if I do gas.v, and then I do gas.r, 0 is less than, okay, let's say 2.5, so I should get a few of them. See, I get all the velocity vectors of my particles that have a next position that's within 2.5 of the left wall. Okay, and then if I do this, it's going to give me all of the x components of their velocities. And then if I do this times -1, it inverts the component of the velocity. So that's what's going to make the particles bounce off the other side. So now I've added the rest of the code that handles the 3 other cases. So this is for particles colliding with the right wall. So now we need to check for particles that have an x position that's within a distance self.radius of the wall that's at position L. Okay, and then I do the same thing for the collisions with the bottom wall, and I do the same thing for collisions with the top wall. And so that allows me to handle the collisions between the particles and the walls correctly. So the last thing we need to do is we need to handle the collisions between particles. So this is definitely the most involved step of the animation and is also the most expensive thing. So particle collisions. Okay, so to handle these collisions, what we need to do is we need to find the pairs of particles that are colliding with each other. So we need to find the particles that are at a distance of less than twice the radius of each other. So if we look at these balls on the figure over there, we see that the collisions happen when basically 2 balls are pretty much touching. Okay, so we need to find when the particles are at that distance. And we need to loop. So what we basically need to do is we need to loop through all the distinct pairs of particles and do this check. So we're going to do this with a double for loop. So for I in range self.n, and for j in range so I plus 1 self.n. So this ensures that I'm only looping through the different particles I and j that are not the same. Okay, and then what I need to do is I need to check if the distance between particle I and j is less than twice the radius. So if np.linalg.norm, so r next I minus r next j is less than twice times self dot radius, well, what we need to do is we need to update the velocities of particles I and j using the formulas that I've shown you above. Okay, so remember, we're looping through the particles, we're finding those that are close to each other that are going to undergo a collision. Okay, and once we found them, we need to change their velocities to make sure they get deflected. And we need to do this at each time step of the animation. Okay, so if we look at these formulas, we see that it involves difference between the velocity vectors and the difference between the position vectors. So I'm going to define some new variables. So I'm going to say rdiff equals self.ri minus self.rj, and vdiff equals self.vi minus self.vj. Right, and then I'm just going to implement these formulas over there. So self.vi, so the velocity of particle I is going to become self.vi minus, so rdiff dotted with vdiff over rdiff dotted with itself times rdiff. Okay, so that's how we update the velocity of particle I. And then we need to update the velocity of particle j. Okay, so let's do this. So let's just look at the formula again because we have to be a bit careful. Right, so we see that for vi prime, right, for updating the velocity of particle I, it was vi minus vj times ri minus rj. And here it's vj minus vi times rj minus ri. So the minus 1 gets cancelled that we pick up. But here it's rj minus ri. So basically this is minus of that one. So we have to put a plus sign over there and leave this as ri minus rj, or as rdiff. Okay, so let's do this. So we just need to change this to j, and then we need to add a plus. Okay, and now we've basically got the code that handles the particle-particle collisions. So as I said, this is actually the most expensive step of the algorithms, and there are way more efficient ways to do this, but I think this is the most simple and intuitive way to do it, so I'm just presenting this method in the video. So now that we've been able to do this, we're actually pretty much done with the algorithm. We've actually done the most difficult bit, and I've just added 3 more functions. So this one is called step, and it basically computes the positions of all the particles at the next step. So all it does is it calls check collisions to update the velocities, right? So it updates self.v, and then I update self.r by integrating the equations of motion, as I said before, right? So self.r plus equals self.v times self.dt, the small time step. Then I have this function called animate, and this function basically evolves the ideal gas simulation for the specified number of states, and it returns the positions and the speeds of the particles at each time. Okay, so to do this, all I've done is I've created an empty positions array of shape n steps n and 2, and that stores the position vectors of the n particles for every time step. And then I've done this also for speeds. So I have a bunch of zeros of shape n steps and n, so I'm storing all the velocity norms of my particles. So we're going to use this to check with a Boltzmann distribution. And then I'm just basically looping through each, for each time step, I'm appending the positions to the position array, I'm appending the velocity norms to the speeds array, and then I'm stepping my animation. Okay, and basically when I run this, it gives me an array of the particles' positions and speeds at all time. Okay, so this is the function that basically evolves our ideal gas. And then the last thing I've done is I've written this function called Maxwell-Boltzmann, okay, and it computes the Maxwell-Boltzmann distribution for this system. Okay, and remember we need this quantity kBt, which is the average kinetic energy per particle, right? And basically we find this by doing half mv squared for all the particles of velocity v0, right? So this is kt at time t equals 0. And what we're basically going to do is check if our animation is consistent with these results. Okay, so now that we've done this, we can actually do our simulation. So let's do it for 400 particles of mass 1 kilogram, radius 0.2 meters, in a box of length 20, with the same initial velocity that we chose before, and for a duration of 10 seconds and with 750 steps. Okay, so it's going to be a pretty big box. Okay, so then what I need to do is I need to create arrays called positions and speeds. That's just going to be gas.animate. Okay, so we need to run this cell, and it does take a bit of time to run because there's a lot of things to do. So let's do it. Oops, oh, I forgot to run this guy. Okay, so let's just rerun this. Right, now it should run. Okay, so the code's done running. So as you see, it took about 2 minutes and 10 seconds. And remember, this is because at each time step, we have to compute all these pairwise distances, and that basically means we have to do about n squared operations at each time step, right? So as I said, there are way more efficient ways of handling the particle-particle collisions, but this is just for demonstrating how this works. Okay, so now we've got the positions of our particles at each time, the speeds of our particles at each time, and one thing we can do before we actually write up the animation is to check that the total kinetic energy of our system is conserved. And that's a way of checking that our results are consistent, right? So I'm just taking the speeds at time 0, and I'm comparing the sum of the squares of the speeds at time 0, and I'm comparing it to the sum of the squares of the speed at the last time. And normally we should get something pretty similar, right? So you see we get basically the same result. Okay, so now we just need to add a block to implement the animation. So I've basically added this block to do the animation. So all I'm doing is I'm calling the function Maxwell-Boltzmann to get the plotting data, and then I initialize a figure with 2 axes. So the first axis is going to be to plot the evolution of the gas to the animation, so the ideal gas particles bumping with each other and the walls. So this is what I'm doing here. So at each frame, I just scatter plot these positions, and then we just have a histogram on which we're going to plot the speeds of our particles at each frame, so at each time step, and we also plot on top of it the Maxwell-Boltzmann distribution. Okay, and then all I do is I do the standard animation code, and so let's run this and see what we get. Okay, so the code ran. Let's see. So we have our animation over there, so let's run it and see what we get. Right. Okay, so we see that we basically, on the right, we have our ideal gas. So we have our molecules bumping, our particles bumping into one another. And here we have a plot of the velocity distribution of our particles, right? So this orange curve is the Maxwell-Boltzmann distribution, right? And we see, so let's replay it from the start again. We see that our system converges to the equilibrium very quickly, right? So it starts to fit this curve really nicely. And this is basically how we've verified the Maxwell-Boltzmann distribution with our simulation. So thank you very much for watching.